All right, welcome back. So here we are. We're going to deal with linked binary search trees again. And we're using the linked list. And essentially, we're going to create two functions. One is going to return the height of the tree. And the other is going to return if it is a balanced tree or not. So if it is balanced, it'll return a value of true. Okay, so let's go see where they want us to put it. If they gave us a little spot on what they've got. We're looking for height or is balanced. Not seeing one yet. Would be down here. So let's come down and indent in along the same indentation line as replace. Def height. And the height of the object itself, so we're going to pass the object to it. And it returns the height of the tree and height of the tree. It's the length of the longest path. That's from the root node to the, I shouldn't say the, to a leaf node. And when I say a leaf node, it is the one leaf node that is furthest from the root node. Go ahead and bring that in. You know what? A little bit more. We got a precondition. The precondition is when of t greater than 2, t dot height is equivalent to 0. Okay. Got comments in there that we need to, so basic housekeeping, if you will. Okay. So for height, let's go ahead. It's going to be a recursive function that we're going to have to create. Because we're going to have to go back over and over again looking to see what's going on. It's not just going down one path. We've got to check all the paths to find out which one's the longest path. So let's go ahead and define this recurse. I'm going to pass it a node. And if node is equivalent to none, return 0. Else, else I'm going to return 1 plus max, call this recurse no dot left, comma, recurse node dot right. Now, essentially what we're doing here is a divide and conquer kind of logic. We're calling both of them, left and right, and finding out which one is max of the two. So it's a recursive call, but it's also, we're doing a divide and conquer at the same time, so we're doing two at the same time. So with that said, come down, so H equals recurse self dot root if not self dot is empty H minus equals 1 turn H. And H is what we're looking for, is the height. So that's what we need for this one. Let's go do the def, see if it's balanced. And balanced in Module 10 lecture. What it means to be balanced, and have an assignment in Module 10 relative to looking at a binary tree and saying, is this tree balanced or not? So at this point, you know what balanced is and what is not balanced. So default comments we're going to put in here. What does this return? You know what? I don't want to get that complex. Let's just say it returns true if the tree is balanced, or false otherwise. Okay, it's pretty straightforward. You know what? Hang on. What are the criteria for it being balanced? And let's say T is balanced, tree. It's balanced if T dot height is what they said over here in the instructions. So that function is less than 2. So 2 times the log when self plus 1 to 2 minus 1. All right. So with that said, let's just returns return I want this. Self dot height less than 2 times log. There we go. That's what we had to have here. So that's if it's balanced. Tell us, is it balanced or not? Okay, and it's just a calculation. And let's test to see where we stand with this. We're golden again. All right. At this point, you know what balanced is, but this is the calculation for this class to go do what it's got to do. And mathematically, using Python, determine if it is balanced or not. You can look at it and tell if it's balanced, but we're not looking at these things. These things could be massive. And when they are massive, we just run the code and it does it for us. All right. See you in 10.3.